So let's say that we have a potential that is symmetric, finite potential. So we have, say, V naught. That's V naught. Then we have 0. Then we have V naught again. So this is X. I guess we can call this, I don't know, X naught and maybe 2X naught or something like that. This is X naught. This is sort of twice that, but imagine it's shifted a little bit more to the right. So finite well, and let's imagine a superposition, a wave function at t equals 0, which is an equally weighted sum of the ground state and the second excited state, something like that. And we want to think about psi of x and t. Let's draw these functions. So psi 1 of x x naught, 2x naught. What does that look like? Well, if we choose the positive one, then we have to respect the symmetry. So same height here and here, bending toward the x-axis, something like that. And then we're going to come down with exponential decay, trying to make it symmetric. Psi 3 of x, what does that look like? X naught and 2x naught. One node for psi 2 of x and 2 nodes for psi 3 of x, even function, right? So we have to come to the same point. If we choose positive, then we're going to bend such that we come down to, here at the midpoint. So we're going to do something like that. And then I'm going to reflect that, right? It's an even function, so I'm going to reflect that across there, something like that. This should be about the same height as that. It's not quite like that, but... And then we have exponential decay from there. Same thing over here. Again, an even function, and we're considering a superposition of that. So psi of x and t is 1 over root 2. Psi 1 of x, e to the minus I, e1t over h bar, plus this one for psi 3 of x. And what e1 and e3 are. First of all, we've made an assumption that for this potential, for that height, there's at least 3 bound states. So there's E1, E2, and E3, and the values of these energies will depend on the intersection points. We're assuming there are at least 3 intersection points between the functions, alpha over k, the tangent and cotangent of KL over 2, or in this case, k x naught over 2, because that's the depth of the well. That's the width of the well, sorry. So what kinds of things can we conclude about this superposition? Well, let's consider the expectation value of the position. Oops. Expectation value of the position. Even functions. So none of the terms in psi of x and t, or the probability density, those terms don't, they can't prefer one side of the well over the other. So this has to be the well midpoint. And so what's the well midpoint? 1.5 x naught, so it's 3/2 x naught in this case, and that's independent of time. So despite the fact that there's a frequency of oscillation, right, the probability density is oscillating in such a way that it's always an even function, and so that must be fixed, time independent, and therefore it's also true that this is time independent. In fact, it's 0. Right? We can get that from Ehrenfest's theorem by taking a time derivative of this. And we can say also that minus infinity to 3 halves 3x naught over 2, right, to the well midpoint, is of psi x t modulo squared, right, the integral of the probability density, right, the probability of being to the left of the well midpoint, that given that this is an even function, that has to be, well, that has to be equal to the probability of finding the particle on the other side, so of the well. And so both of these must be equal to a half. And therefore we can say, we can also conclude that this quantity, x naught to 3x naught over 2, psi xt modulo squared in the x, the probability of finding the particle on the left half but inside the well, this is time dependent. This is time dependent. So let's just say time dependent. So being on anywhere to the left of this is is a half. So if the probability increases to the left of x naught, then the probability in here will decrease. So this will be less than a half, but it will vary in time.